Hello, this is Math Jazz from All Is Cool, and I am here with another live stream. Today, we're going to be talking about linear functions. And of course, as always, if you have questions, please email them to me and I will answer them. Or you can type them into chat as well. So, let me pull up email accounts so that I can be ready for your questions. The email for this page is mathjazz9@gmail.com. Okay, so today we're going to be talking about linear functions. So this might be something familiar to all of you from high school or from your algebra class whenever you took it. So, but we're going to go through this nice and slowly. Okay, so we're going to define a linear function to be a function that has this equation, okay? It's a real function. Too wide. There you go. Linear function is a function that is of the form f of x equals mx plus b. Okay? Now, the graph of something like of a function of this form is going to look something like this. We'll have the point 0, b, and we will have function will look like a line, thus linear, and its slope will be m. This is our function f of x equals mx plus b. Now we have some special terms that, in fact, I've already used one of them. We have to talk about the slope. The slope of our function is going to be m, and the y-intercept is going to be b on our function. Now, we're going to have to define what an intercept is. The intercept so the y-intercept of a function is the point where it crosses the y-axis. We obtain this point by plugging in 0 for x. It's called the y-axis, or sorry, it's called the y-intercept because it intercepts the y-axis, it crosses it. So on our diagram, that point is here. The y-axis, of course, is the vertical axis. And the x-axis is the horizontal one. So, analogously, the x-intercept well, that's going to be the point or points because you can have more than one x-intercept on a function. but it's the function where, sorry, is the point where the function crosses the x-intercept. Sorry, crosses the x-axis. There we go. It's also called the intercept because that's where the function intercepts the axis, or where it crosses the axis, where it touches the axis. And so there are terms that we need to know, but the reason that the terms are what they are isn't necessarily very complicated. Okay, so, well, I claimed that b in this formula, in this equation here, this function, that b represents the y-intercept. I defined the y-intercept to be the place where the line crosses the y-axis, and so we need to prove this. So how do we prove that? Well, the y-axis is the line where the x-coordinate always equals 0. So what we do is we take our generic f of x, our generic linear function f of x equals mx plus b, and we want to plug in 0. So if f of 0 equals b, then our y-intercept is b. Let's check that. M times 0 plus b is in fact equal to b, because 0 plus b is b. So this checks out. We just proved that b is in fact the y-intercept of our linear function. Okay. So then the next thing I want to talk about is that this form here that we use to define a linear function has a name. This is called the Slope-Intercept Form. And there are other forms that a linear function can come in. One that I find very useful is called point-slope form. So here is the point-slope form. It goes like this: y minus y1 equals m times x minus x1. And I claim that this is a line that is, that any function that has a graph that satisfies this is going to be a function that satisfies this. So every graph from an equation of this form is going to be able to be written as a graph of an equation of this form, or it is exactly going to match up with a graph of some equation of this form. So, and then there's a way to algebraically convert one equation into the other. That's what I claim. If that is true, then it makes sense to have these, to call these two forms of the same function, instead of calling them different functions or graphs altogether. Okay, so with that, I also have a few other claims. So that was my first claim. My second claim is that m is the slope of this when it's written as a line. Or when written in slope-intercept form. And 3, that this line passes through the point x1 comma y1. Okay, and we're going to prove all of these things now. So first thing to prove, that y minus y1 equals m times x minus x1 is able to be written in slope-intercept form. So is a line, as we've defined a line so far. So let's rewrite this as y equals m x minus x1 plus y1. Okay, and then let's distribute this m. So y is equal to mx minus mx1 plus y1. And then this is equal to mx plus negative mx1 plus y1. And this is a number, so we can name it b. And now we have that, well, y is equal to mx plus b. And we have a line. So that's our first box ticked off. It is a line. The next thing that we wanted to prove was that the slope of our line was m. Well, this slope-intercept form, as we manipulated it, we got down into the form mx plus b, which is the form of a slope-intercept line, and the slope was m. So that means that the use of the letter m here in point slope form matches the use of m in this equation here in slope-intercept form. So we can say that m is the slope of this line. And the last thing that we needed to prove, so this is our second checkbox that we can tick off. The final checkbox that we need is we need to know that we hit the point x1 comma y1. So the way that you check to see if an equation hits a certain point is you plug in that point. So y, here's our formula. We're going to plug in x1 for x and y1 for y. So we get y1 minus y1 is equal to m times x1 minus x1. If this is a true statement, then the point lies on the curve that's represented by this equation. So, well, we get 0 is equal to m times 0, which is 0. So we check that off. All three of our conditions are met. So writing out this point slope form gives us a line, and it has a slope that we can predict, and it goes through this point that we chose, which is the point x1 comma y1. Now there is one more thing we want to prove. We proved something that's called the forward direction here, which is that point slope form can be converted into slope-intercept form. But what we want is called the reverse direction now, to just make sure that everything is equivalent. Now, we proved every time we're in one form we can convert to the other, but we didn't prove that if you're in the other form we can convert back. So what we want for our last condition, and this is a condition on slope-intercept form, so y equals mx plus b, we want to prove that this here, which we claim is a line with slope m and travels through the point 0b, we want to show that if we use point slope form, we get the same line as we get using slope-intercept form. So let's try this out. Slope-intercept form says y minus y1, which is b, is equal to m times x minus x1, which is 0. And when we add b to both sides, we get y equals m times x minus 0 plus b. And when we simplify what's inside the parentheses there, we get y is equal to mx plus b. And that checks off that not only can we go one way and convert from every property we want of of point-slope form is satisfied, but also slope-intercept form matches up with it as well. So when you pick a point, or when you pick an intercept and a slope, you can plug that into either form and it will convert into the other form nicely if you need it to. Okay, so that might seem a little pedantic, but it's important to make sure that everything works the way that you expect it to. Okay, so with that, let us go on to systems of equations. Okay, so let's say we have two lines and we want to figure out where they cross. Okay, so we have two lines. Let's say y equals 3x plus 5 and y equals negative x minus 2. Okay, so we have two equations. I'm going to use this brace here to group them together to represent that they're in the same problem, that we want to have some property that relates to both of these lines. And in fact, what we want right now is to figure out where both of these lines cross. So, if a point lies on a curve or a line, when we plug that point into the equation for that curve or that line, we need to get a true statement. If we have a point that lies on both of these lines, then that means that the point has to satisfy both of these equations. So what we want is we want to be able to figure out when a point lies on both equations. And the way to do that is we need to have the x value. What we need to do is we need to figure out an x-y pair such that when I plug the x value into each of these equations and the y value into each of these equations, it balances. So if the y value on this curve equals the y value on this curve, that means that this y equals this y. So we have this expression equals y, which equals y, which equals that expression. So I can write, if I'm trying to find the place where they intersect, I can rewrite this as 3x plus 5 equals, let's zoom in maybe a little bit, 3x plus 5 equals negative x minus 2. And I want to bring all of my x's to the same side of the equation, so I add x to both sides and I get 4x. I want to bring all of my non-x's to the other side, so I subtract 5 from both sides and get negative 7. And that means that x is equal to negative 7 over 4. So this, negative 7 over 4, is my x coordinate of the point where these two lines intersect. And now I want to figure out, well, if I plug in my x value to one of these lines, I should get out a point. And that point will be the point of intersection. I'll get out a y value, which will be the y coordinate of my point, and I can then I can then use my x and y coordinates to determine the point where these two lines cross. So let's go y equals negative 7 over 4 minus 2, which is going to be equal to 7 over 4 minus 8 over 4, which equals negative 1/4. That is our y coordinate. So the point of intersection is equal to negative 7 over 4 comma negative 1 over 4. This is our point of intersection for our two lines. Okay. Now the method that we used here is called substitution. What we did was we substituted this expression for y into this equation. So the other method to solve a problem like this, the other big method to do it, is called elimination. And so let's come up with a system to work on. Let's have y equals 4x minus 3 and y equals 2x plus 2. So I want to find out where these two lines cross. And the way I'm going to do it is, well, if these two things are equal to each other, and those two things are equal to each other, that is, the right and left hand side of the top equation are equal and the right and left hand side of the bottom equation are equal, then if I subtract the second equation from the first, I've subtracted equal things from each side of the equation, and I should be left with things that are equal. So y minus y is 0, equals 4x minus 2x is 2x, and 3 minus 2 is negative 3 minus 2 is negative 5. Now from here, I'm going to add 5 to both sides, and then divide by 2. So I get 5 halves equals x. That's my x-coordinate of the point where we intersect. And from here, I'm going to plug this into this equation. I could plug it into either, but I'm choosing this one. So I get y equals 2 times 5 halves, because that's our x value. We have 2 times x plus 2. The 2's will cancel. I'm left with y equals 5 plus 2 is 7, and that is the y-coordinate of our point. So our point of intersection is going to be 5 halves, comma, 7. Okay, so this doesn't seem so hard, but I guess the next thing that we might want to talk about is when we have more than 2 dimensions for our relationships between variables. So what we've been doing so far, we've been finding intersection points between 2 lines. So here's a line, and here's a line, and here's our point of intersection. But we've only had an x and a y. 2 variables means 2 dimensions, and so we have these 2 functions, these 2 lines, linear functions, and we've been finding their points of intersection. But we can have multidimensional relationships between several different values, different variables. So this is my best attempt to draw an x, y, z coordinate system. So this is our ground here, the xy plane, and this is our vertical direction, z. So if you can imagine having, like maybe a book here. This book is resting on the xy plane. If the xy plane were a table, then this book would be sitting on the same level as that table, and I could drag it up higher, or I could push it down lower. The up and down direction is the z-axis, whereas the x and y directions are flat, like moving side to side on a table or forward or backward on my table. This. and then z is moving up off the table or down under the table. Okay, so we have this, and well, what does it mean to be linear when you have more than two variables? Well, turns out the nice generalization of linear is going to be if all variables are raised to the first power only. Then we have a linear function of more than two variables, or however many variables we have. Okay, and so the way that we want to think about this is that, let's say we have a line, so y equals mx plus b. What we can do with this line is we can rewrite it as y minus xm, mx equals b. And we have all of our variables on one side of the equation, and then our constants on the other. This is called standard form, or standard form of a line. Notice that all of our variables are being raised to the first power only. And so we have just a sum of variables times their coefficients. Oh, and one more thing is that we can't have two different variables multiplied by each other. So no terms with products of variables. Okay. So if we do this, if we have this idea of a standard form of a line, which is all of our variables on one side, each variable raised to the first power, no two variables multiplied by each other, and the other side we have constants, then we can generalize to multidimensional linear functions. So, for example, we have like x minus 3y plus z equals 5 is a linear function. It's a multidimensional linear function, and by that I mean that there are more than two dimensions. But it is a linear function. And instead of being graphed, our x and y linear functions look like lines like that. Our multivariate functions, our multivariate linear functions, are going to look like planes. So if I can draw a plane, which I might not be able to. This is the graph of a three-dimensional linear function. Okay. So we can go from here and we can start talking about having intersections between planes and trying to determine where two planes intersect or three planes intersect, or if we have more than three dimensions where these higher dimensional planes, how many of them intersect, and if they intersect at a point or if they intersect at a a line, or if they intersect on something with a bigger dimension than that. And, well, unfortunately, we're out of time for today, so we're going to have to talk about higher dimensional lines on Friday. Or higher dimensional linear functions. So come back tomorrow if you'd like to learn more about linear functions, particularly higher than two-dimensional linear functions. And with that, we will end the live stream. Thank you for watching. Hope you're having a great time learning mathematics. And if you have any questions, please send them to my email and I will answer them in my live streams. So have a great day. Bye.